Hi everybody, this is Mr. Zarzak, and in this screencast I'm going to discuss problem-solving approaches for freefall problems concerning velocity and displacement. This question set includes a couple different problems that relate to money to make these problems a little bit more familiar to you, problems that you should be able to think through. So for example, here number 1 says Aunt Minnie gives you $10 per second for 4 seconds. How much money do you have after 4 seconds? Giving this a little thought, I bet you can figure it out. Let's pause the video and just take a second to do just that. And hopefully after a little bit of thinking, you realize that after this 4 seconds of time, you will have $40. Okay, so let's apply this line of thinking to solve a physics problem. It says here a ball dropped from rest picks of speed at 10 meters per second. After it falls for 4 seconds, how fast is it going? Alright, so what this is an application of our instantaneous velocity equation, which says v final equals v initial plus acceleration times time. Now, if we look over here, okay, they tell us in the problem that our initial velocity is equal to 0. So it says ball dropped from rest. Okay, in which case, that initial velocity shrinks to 0, and this just becomes a simplified version, or what we learned in class is the Freefall equation, which is instantaneous velocity equals acceleration times time. So this right here, this would be our symbolic equation. Substituting in my values, okay, 10 meters per second, that's the acceleration of gravity. So I can write that as 10 meters per second squared. All right, and we're told that this ball's going to fall for 4 seconds. So 4 seconds in here. 10 meters per second squared times 4 seconds gets you a final velocity of 40 meters per second. Okay, so our basic approach of symbolic equation, substitution of value with units, answer with units. Okay, so now getting back to money style problems, it says you have $20 and Uncle Harry gives you $10 each second for 3 seconds. How much money do you have after 3 seconds? Alright, so again, I want you to be able to reason this through. $20 to start with and $10 each second for 3 seconds. So hopefully a little bit of thinking, you come up with, after this 3 seconds of time, you're going to have $50. Alright, now we're going to take and apply the same thought process to another physics problem. Okay, instead of money, we've got a ball thrown straight down with an initial speed of 20 meters per second. After 3 seconds, how fast is it going? Alright, so this is again our instantaneous velocity equation, v final equals v initial plus acceleration times time. V final is equal to our initial speed, that's at 20 meters per second. So 20 meters per second plus our acceleration. Now, we're not told the acceleration specifically in the problem, but because the ball is thrown, once it's in the air, the acceleration is 10 meters per second squared down due to Earth's gravitation. So I'm going to sub in 10 meters per second squared. There's gravity. All right, and we're told a time of 3 seconds. So we'll just sub that in for the time. And we wind up with, let's see here, 20 meters per second plus 10 times 3 is 30 meters per second. So the speed of that ball after 3 seconds is 50 meters per second. Alright, so here we have another money problem. It says here you have $50 and you pay Aunt Minnie $10 per second. Easy come, easy go, huh? It says, when will you run out of money? Okay, so once again, thinking it through. Okay, I want you to be able to reason through this kind of problem, and with a little bit of thought, you might want to pause the video to think. You realize that we're going to run out of money after a time of 5 seconds. Okay, so let's apply this line of thinking to do another physics problem. All right, it says here you shoot an arrow straight up at 50 meters per second. When will it run out of velocity? All right, so once again, we're going to be working with that equation Vf equals Vi plus acceleration times time. Now, we're told that we shoot the arrow straight up at 50 meters per second. So that right there, that's our initial velocity. Okay, so I'm going to sub that in, 50 meters per second. All right, and the problem says, when will the arrow run out of velocity? So what that's really saying is when does this final velocity, or when does this instantaneous velocity become 0 meters per second? All right, well, 0 does not equal 50, so something's got to cause the 50 to change into 0. And that something is the acceleration of gravity. Okay, when we throw a ball in the air, or in this case we shoot an arrow, on the way up, gravity takes away the speed of the arrow because, well, the direction of gravity is down, which is in opposition to the direction of the initial velocity is up. All right, so the way that we show that mathematically in our equation is when we sub in for the acceleration of gravity, because it points in the opposite direction of our initial velocity, we don't sub it in as 10 meters per second squared, we sub it in as negative 10 meters per second squared. Okay, I know that's a little confusing, especially at first, but you can see that the initial velocity is up while gravity always points down. The way we show difference in directions with positive and negative signs. Okay, and in this case, our unknown is the time. All right, so here's the equation. This is what we need to solve. All right, so let me just rewrite this a little bit simpler here. So 0 is equal to 50 minus 10 times t. All right, and here's our algebraic expression. Okay, so I'm going to move the 10 over to the other side by adding it to both sides of the equation. 10t is equal to 50, and if I divide 10 by both sides of the equation, I get my answer of 5, and because I've solved for this time, this is a time of 5 seconds. Question 7 here says, so what will be the arrow's velocity 5 seconds after you shoot it? All right, so all this is doing is just giving us a different perspective on question 6. Okay, again, this is a case where we're going to apply VF is equal to VI plus AT. Okay, and as you're looking at this, some of you are realizing that there's no surprises here. Rather than use this equation to solve for a time, okay, well now if we give a time, just to kind of prove it to ourselves, that the arrow will in fact run out of velocity after 5 seconds. If I sub in that initial velocity, the arrow is 50, negative 10 meters per second squared for gravity, and a time of 5 seconds. All right, and as we're working these in the beginning, you can't see these enough. Okay, the more practice we have, the better you're going to get at these. So VF is equal to 50 meters per second. Okay, there's a plus and a negative 10, so I'm just going to pull that negative sign out in front because we're going to do subtraction. And 10 times 5 is 50 meters per second. Okay, and we get exactly what the problem seems to be hinting at, which is 5 seconds later, the arrow has stopped moving up. What's really useful about this velocity equation is we can apply it for any time we want. So here it's saying what will be the velocity of the arrow 6 seconds after it's shot. So the approach is exactly the same. Okay, VF is equal to VI plus A times T. So VF is equal to that, still just that same initial velocity. It's the speed at which the arrow was shot. So it stays at that same 50 meters per second. Plus the acceleration of gravity. Okay, so the arrow gets shot up, gravity points down, so 10 meters per second squared with a negative sign to show the direction of down, and I promise it says 10. And if I sub in for a time of 6 seconds, okay, well now look what happens. VF is equal to that 50 meters per second, and again I'm going to pull that negative sign out because we are going to do a subtraction, but now I've got 10 times 6, so we've actually got, look at this, 60 meters per second. And so I wind up with a final velocity of 50 minus 60 of negative 10 meters per second. The fact that this final speed has a negative sign in front of it tells us that the arrow is now on its way down. And if we look here where times 6 is, you can kind of see we've traced out the path of the arc of the arrow, and now we're past that peak height. Okay, so the nice part is that the sign of our answer tells us the direction as well as the magnitude. And if we keep going here, one more question about time and velocity. It says here, what's the velocity 7 seconds after it's shot? Okay, and just like before, exact same approach. V final equals V initial plus acceleration times time. How fast and which way is it going? When we shoot it up at 50 meters per second, and the whole reason it comes back down at all is because, well, gravity brings it back down by causing it to accelerate at 10 meters per second squared and down, which we show with a negative sign. So 7 seconds into the trip. Okay, so I'm just subbing in for that time of 7 seconds. V final equals 50 meters per second minus 10 times 7, so that's 70 meters per second. So V final equals negative 20 meters per second. If we look at what our answer is telling us, okay, well, the speed is 20, the velocity is negative 20. The negative is there to tell us that the arrow is moving down again. And just kind of like before, okay, we're tracing out the path. At 5 seconds, we hit the peak. 6 seconds, we're coming down. Now look at where we are here at 7 seconds. All right, we're farther down than we were at 6 seconds. And as the arrow comes down, okay, well now, because the arrow is moving down and the acceleration of gravity is also down, well, if acceleration and velocity are in the same direction, well, now the acceleration of gravity is going to speed up the arrow. Whereas on the way up, the acceleration of gravity was causing the arrow to slow down, slow down, slow down, slow down. At 5 seconds, it would stop. Well, now on the way down, it's causing it to speed up, speed up, speed up, speed up, speed up. Okay, gravity takes away its speed on the way up, and it gives it right back on the way down. That's pretty neat. All right, so how fast and which way it's going is one thing, but what about where is it, that's displacement. Okay, so this first question says here, velocity is one thing, displacement another. Where is the arrow you shoot up at 50 meters per second when it runs out of speed? All right, and Olivia over here in the corner, she's got a thought bubble above her head, and she's given us some hints as to what we need to do to solve this. All right, this is a two-part process. First, we got to calculate the average velocity of the arrow, and then we'll use our average velocity times time is equal to displacement, which is a fancy way of saying speed times time is equal to the distance. All right, so looking at given information here, all right, well, we have the initial velocity of the arrow, that's at 50 meters per second, and when it reaches that peak height, when that velocity shrinks to 0, that's 5 seconds into the trip. All right, if we calculate the average here, all right, well, they tell us over on the side that the average velocity is just the initial plus the final divided by 2. All right, so I'm going to go ahead and I'm going to calculate that. So V average equals V initial plus V final divided by 2. And I'm writing the equation just to get in the habit more than anything else of always writing an equation before calculating. So let's see here, average velocity. All right, my initial was 50 meters per second. My final is 0. So I'm going to take that and divide by 2. So that makes my average velocity, let's see here, 50 plus 0 divided by 2, that is 25 meters per second. All right, and then the little thought bubble says, hey, displacement is equal to average velocity times time. So I'm just going to write that out in a different color here. D is equal to average velocity times the time. D is equal to that 25 meters per second. All right, and we had reasoned out before that it's going to take 5 seconds to reach that peak height. So 25 times 5 is 125 meters. At its maximum, the arrow reaches a height of 125 meters above the ground. All right, question 2 for freefall displacement wants to know how high we're in the air 7 seconds after being shot up at 50 meters per second. Now notice that 7 seconds is somewhere below this peak height, which occurred at 5 seconds that we calculated in question 1. So one thing to think about is that when we get our answer, we're going to look for something less than 125 meters. All right, so as far as calculating goes, okay, we're going to say take the same approach as we did before. All right. We're also going to take advantage of the fact that, well, we already went through the trouble of finding the velocity of the ball 7 seconds into the trip. Okay, we calculated that back in, what was that? That was question number 9. Okay, we found that the ball was, that the arrow was moving at 20 meters per second down. That's the negative sign. All right, so something changes here, and that's the average velocity. So I'm going to go ahead and calculate that. So I got V average is equal to initial plus final divided by 2, and I'm going to write that equation every single time. So average is equal to, okay, still started at 50 meters per second. All right, but now my final velocity is negative 20 meters per second. I'm going to take it, I'm going to divide that by 2. Sorry, that's a little messy. Okay, so let's see here. V average is equal to, all right, 50 minus 20, so that's 30 meters per second. divided by 2. Okay, so different time frames, so different average velocity. So if the average for that 7 seconds is 15 meters per second. All right, and now that I have this average velocity, okay, I'm going to apply that displacement is equal to average velocity times the time. D is equal to 15 meters per second times a time of 7 seconds. And if I calculate that out, let's see here, 15, 30, 45, 60, 75, 90, that is 105 meters. Okay, so less high above the ground than it was at 5 seconds because, well, at 7 seconds the arrow is on its way down. Okay, so let's change the scene up a little bit. Now we've got Aunt Minnie, and she drops a penny into a wishing well, and it falls for 3 seconds before hitting the water. It says here, how fast is it going when it hits? All right, and so notice over here that there's this little down arrow with a little positive symbol. It says anything in the downward direction for this problem, make it positive. Okay, we've also got Kelsey over here. She's given us some other equations to consider. These are our free fall equations for both speed and for distance. All right, so this one says here, how fast is it going when it hits? All right, so that's a case, all right, where we're interested in VF equals AT. Speed is equal to acceleration times time. Okay, so let's see here, the speed, if gravity accelerates us down at 10 meters per second squared, all right, and it falls for 3 seconds, all right, before I calculate, not that that's too tough, all right, again, notice that we're talking about down being positive, okay, so now I'm plugging in gravity as a positive value because we're told this reference in the problem, use down as positive, so if it tells us to use it, we got to use it. All right, so let's see here, so VF is equal to 10 meters per second squared times 3 seconds, that is just 30 meters per second. Here in part B, it says what's the penny's average speed during its 3-second drop. Okay, kind of key word there is that we drop, in which case the initial velocity is equal to 0 meters per second. In part A, we calculated a final velocity of 30 meters per second, in which case we can calculate an average velocity as the sum of the initial plus the final velocity divided by 2. Average velocity is equal to 0 meters per second plus 30 meters per second divided by 2, which makes the average velocity 15 meters per second. All right, hopefully as you're seeing more and more of these, how to calculate these values is becoming a little more second nature for you. All right, and part C here says how far down is the water surface? All right, so in part B, we calculated this average velocity as 15 meters per second. All right, and it takes 3 seconds for the coin to make it down to the bottom of the well. So we've seen this a couple times now where if we want to know how far, we just take that average velocity, multiply that by the time, so D is equal to that 15 meters per second from part B times the time of 3 seconds. All right, when we calculate here, we get a distance of 45 meters, okay? And so there's nothing wrong with that. It's a perfectly correct answer. All right, but notice that, well, Kelsey over here, she's got another equation for us. So there's another approach, all right? So I just wanted to show you how we can apply free fall distance equation to also solve for this 45 meters. D is equal to 1/2 AT squared. All right, so look at this, look what happens. So 1/2 acceleration, that's just gravity. That's what makes the coin fall down there to begin with. So 10 meters per second squared. And notice, once again, I'm plugging this in as a positive value because we got this arrow here. So anything down, we're going to make positive in this problem. All right, that time, it still takes 3 seconds to get there. So look what happens. All right, 3 seconds squared. So 3 times 3, that's 9. 9 times 10 would be 90, but cut that in half, and look what we wind up with. D is equal to 45 meters. The same 45 meters that we calculated by using the average velocity times the time to get the displacement. We can also use D is equal to 1/2 AT squared. So which of these approaches is better? Well, they both return the same answer, so whatever you're more comfortable with. All right, if you're used to calculating free fall distance using 1/2 AT squared from problems we did before in class, then by all means do that. I mean, it is a one-step substitution and solve. However, if you happen to have the average velocity and you know the time, then why not take average velocity times time to get how far you are? Okay, so I want to show you one last problem just to show you one more new approach, something that we can try here. All right, so it says here, Aunt Minnie didn't get her wish, so she goes to a deeper wishing well and throws a penny straight down into it at 10 meters per second. How far does this penny go in 3 seconds? All right, so we've been working with this approach, all right, where we find the final velocity as some value, and then we use that final velocity to find the average velocity. And then once we have the average velocity, we find the displacement by taking the average velocity and the time. Okay, so there's nothing wrong with that. But we've done that approach now a couple times, all right? Kelsey down here, she's got another way that we could calculate this. How far does this penny go in 3 seconds? And what's nice about it is it allows us to do this calculation as one single step. All right, so this is the full displacement equation. It says how far we are. In order to know that, we must consider where we're moving to begin with, so that's VI. How long have we been moving for? That's T, that's time. So D is equal to VIT. But we must also consider if during our trip, did we speed up or slow down? So that's the acceleration. And again, all these things take time, so we throw the time in there, and then the second term of the time gets squared. All right. So if we look here, we've got this initial velocity of 10. We're keeping down positive. Our time is 3 seconds. And our acceleration, that's going to be due to gravity. So look what happens. D equals VI, which we're told right here is 10 meters per second. So 10 meters per second. All right, it says how far does this penny go in 3 seconds? So I'm going to sub in a time of 3 seconds. To this, I'm going to add 1/2 times the acceleration of gravity, 10 meters per second squared. And one more time, okay, there's that positive arrow, so anything down is positive. So in this case, gravity is the positive value, times 3 seconds squared. Okay, so I know this looks kind of complicated, but it is just one substitution into one equation. So let's see here, what do we have? So we have 10 times 3, so that is 30 meters, plus the second term. So let's see here, I've got 3 squared is 9, times 10 is 90, divided by 2 is 45. So that second term returns 45 meters. Take the two pieces, add them up, 30 plus 45 is 75 meters. And we got ourselves an answer. Now again, you can go through and calculate the final velocity of the penny, use that final velocity to get the average velocity of the penny, and then use that average velocity times that time of 3 seconds. And like again, I encourage you to do that, but you're going to find that the distance that the penny travels is that same 75 meters. So maybe this approach is worth exploring because it saves us a lot of time and saves us a lot of calculation. Alright, so hopefully after watching this screencast, you're a little bit more comfortable with calculations involving free fall, velocity, and displacement. If not, go back and watch it again. This has been Mr. Zarzak. I'll see you in class. Bye-bye.